start with acid-base neutral. Acid-base or neutral. So you should be able to look at any compound and identify it as acidic, basic, or neutral. Let me toss a couple examples up there. And obviously I'm going to solve it according to my style. Crafter, you can kind of figure out if he solves it similarly or differently. All right, so we're going to try to identify these as acidic, basic, or neutral. My style of doing this, if you like to write it out, is say take the compound and in your head or on paper write out the ions separately and then think about what the conjugates of those ions would be. So you write kind of two layers down. First the ions, then the conjugates. Conjugates are usually easiest to identify. So for example, KOH is a strong base. The conjugate of any strong is neutral. HCl is strong acid. The conjugate of any strong, neutral. We said that, neutral plus a neutral. This compound is neutral. If you had to calculate the pH of this compound, you would do, not the ice table, you would write the number 7 down because it's neutral. Done. So no math necessary on this example because it's neutral. Let's try another one. NH4Cl. NH4 plus and Cl minus. Okay, so in this case, the Cl, oh wait, no, it's I, right? I just copied. I minus. Okay, so the conjugate here is HI. Here you could write NH4OH or NH3. Same thing. Okay. Oops, and there's no minus. HI is strong acid, so we've got a neutral here. Let's change color so it's a little easier to see. I minus would be neutral. Okay, NH3. Yeah, kind of a normal base, so this would be a normal acid. So an acid plus a neutral is an acid. I'll just put A for acid. Okay, hi, welcome. How's it going? So, if you had to calculate the pH of this entity, what would you do? This would be an ice table. You would have a K, what would be the subscript? Ka. Should I walk through any of that?
Yes.
Okay, very quickly, if you had to do this, I would write NH4 plus. You write the general equation for an acid. Like that, you draw the ice table. Now, I didn't give you a molarity, but you'd have to be given a molarity, so I'll just put M here. You have to be given that number. You ignore water, the activity is 1, 0, and 0. You go minus X, and you put the plus X where the zeros are, because it'll shift to the right towards the 0. M minus X, X, and X, so Ka is equal to X squared over M minus X. You're going to assume that the X is small compared to M, which is a good assumption for any weak acid. What is the problem when you look up, for my test, it'll be on the back page, when you try to look up the Ka? It will not be there because?
It's a base.
Yeah, it only lists the neutrals. So if you look here on what I would give on my test, NH4 plus is right there, but it gives you the Kb for ammonia, 1.8 times 10 to the minus 5. So you have to convert it by saying this is Kw over Kb. The Kb was the number just off the table there. Where do you get Kw? It's also on the back, 10 to the minus 14. Okay? You solve for this, X will be equal to that X, which is H3O plus. So it's the H3O plus concentration. You take the negative log of that to get the pH. You would expect an answer less than 7, equal to 7, greater than 7. Less than 7. Close to 0, close to 7, somewhere in the middle. Probably, depending on the concentration, probably between 0 and 7 somewhere. The higher the concentration, the closer to 0. The lower the concentration, the closer to 7. Okay, so let's do this last one, the strontium one. I'll write it on the next page. SrClO2, I think. Is that what I wrote? Okay. All right. So we got a strontium 2 plus and a ClO2 minus. This is from strontium hydroxide, and this is from HClO2. Oh, 2. There we go. All right. This is strong base, so this conjugate has to be neutral. What's that? Regular weak acid. Normal acids, that's a normal base. So this would be basic. If you had to find the pH of this, you would do what? Again, an ice table, and you would have K subscript B. So you'd end up, you'd write ClO2 minus plus water. The base grabs a proton, HClO2. Acid loses a proton. So this is the general equation for a base. You'd write the ice table. You'd have to be given, again, the molarity of the weak base. Ignore this, 0, 0, minus X plus. So the setup is pretty much the same. And you wrap KB is equal to X squared over M minus X. You're going to assume X is small because it's a weak base. So you're going to drop out the X and the subscript. What's the problem with KB? It's not going to be given. This is an ion, and the table does not list ions. You would have to look for the Ka of, in this case, chlorous acid, which in this case is 1.1 times 10 minus 2. Go from there. Okay? So again, just the way it's set up, you have to go Kw over Ka to get the K value. I guess that's all I want to say. You'd expect the answer to be greater than 7. Yeah. The higher the concentration, the higher the value, the more basic the answer would be. All right. So that's acid-base neutral. Any questions? Okay. Let's go to the next one. Let's do a little bit of strongest acid and acidic proton. Strongest acid and acidic proton. I think I have some.
Back on that previous problem that you just did, would the solving of X give you the hydronium ion or the hydroxide ion?
Oh yeah, that's good. When you solve for X here, you'll have to note that the X value is going to be the hydroxide ion. Oh, I can see it really clearly, unfortunately. Okay, there we go. That X will be the hydroxide ion, so you're going to find the POH and take 14 minus that. So the POH would be less than 7 because it's basic, and then the pH would be greater than 7. Good, good. Excellent. All right, I was looking for an example of acid-base, comparing acids and bases. We'll do some standard examples first, which I think we have not done these in class. Is that correct? I don't think we've done these in my class yet. So let's start with these. We're going to pick the stronger acid. We'll go through, and then we'll talk about most acidic proton after that. Okay. Which one do you think? The one on the right or the one on the left for the first row? The one on the left because double bonds will lead to resonance. Yeah, if you have resonance, the conjugate base will be stabilized and the original acid will tend to be stronger. Okay. Next one. Right or left?
Right.
I would go with the one on the right. Why is that?
Oxygen.
Yeah, look what's different. The oxygen versus the nitrogen. Now when you're comparing two different atoms, in contrast to the previous, they're all the same atoms. If you're comparing different atoms, you look at your periodic table, as you go to the right and down, your acid's getting stronger. So nitrogen versus oxygen, the oxygen's more to the right. In this case, it's more electronegative. Because it's more electronegative, that'll cause this to be a stronger acid. Next.
Left.
The left-hand side. Yeah, I like that. Again, same reason. Fluorine, it's chlorine and a bromine. So different atoms. You're going to look at the periodic table. Bromine is lower down because of size or polarizability. This will be the stronger acid. Next, right or left? Definitely the left. Why is that? There's more O's. That will likely lead to more resonance. That'll stabilize the conjugate base, making it stronger. So usually, this is similar to the first example. When you see more oxygens and or more double bonds, usually that will have more resonance, making that acid stronger. Last one, right or left?
Right.
Why? The Cl. So you're looking what's different. One has a Cl, the other doesn't. When you have an electronegative atom compared to nothing, not just a hydrogen, the electronegative atom, again, stabilizes the conjugate base, making the acid stronger. So if you see more electronegative atoms in one than the other, that one's going to be stronger. The closer the electronegative atom is to the acidic proton, the stronger the acid will be. So the Cl happens to be on this one if it was the further away against the weaker the acid. So, but this won't be stronger because of that Cl. Okay, any questions on those? Then I want to say a little bit about, what was it? Most acidic proton. Yeah. Define the strongest base. Well, it would have to be written slightly differently because I wrote these as acids. They have extra protons, so a base would have to be all these versions minus the protons. And then you would, if I did that, erase one proton from all of these, you'd pick the opposite answer of all of them. So the base answer is going to be the opposite, because as the acid strength goes up, the base strength goes down, and vice versa. Good clarification. So if you like acid, if you know, like if you prefer studying the acid, do that first. And if that's about the base, select the opposite. Okay, good. Don't do drugs, kids. Okay. So let me now move this out of the way. Talk about most acidic proton. I think I come up with a couple examples for it. Okay. All right. Oh, I'm just really feeling it right now. Okay, let's try that. This is a great one. Love it. Okay. All right, most acidic proton. I'll zoom in on that so it's a little easier to see. There we go. All right. So there's a lot of protons here. Remember, where there's a vertice, that means there's a carbon. So for example, there's a carbon here, here, all around this hexagon, except where the oxygen is, there's carbons. And then there's a carbon down here at the bottom. Carbons, well, when they have a formal charge of 0, have how many bonds? 4. So if you ever see a carbon missing bonds, it means there's a hydrogen there. So for example, I won't do this for all of them, But say this carbon right there, where I put the brown dot, you see 2 bonds. That means we assume, or we know that there's 2 hydrogens there. Okay, so there's a lot of hydrogens here. You want to figure out which one's the most acidic. Let me number some off. There's more than I will number, but we'll just, out of time limitations, 1, 2, 3, and 4. All right, let me give you a moment. You can think about it before you yell it out. I want you to order the acidity of these protons from strongest to weakest. 1, 2, 3, 4. Strongest, weakest. $15 more seconds. That's off. That's off. All right. Strongest. Yeah, I like that. Next. 1, next. 2, and then 3. All right, let's talk about why. Let's start with why 2 versus 3 as far as the weakest goes. Yeah, you're looking, what's the difference between 2 and 3? For 2, the hydrogens are on a carbon. For 3, they're on a nitrogen. Different atoms, you look at the periodic table. Nitrogen is more to the right. It means that hydrogen will be stronger. So when you go to 1, that's on an oxygen. It's 1 more to the right. So that one has to be even stronger. It's more to the right on the periodic table. What's the deal with 4? It'll have resonance. You see oxygens, you see double bonds. Now you could actually draw it out, or just hope you're right and say, oh, it looks like there's resonance. So you're totally right in this case. That would be the order. Any questions? Did you want to do one more harder one? You're good? Okay. You're into it. Yeah. That's good. Good. Okay, I like that one. All right. We want to find the most acidic hydrogen. Remember, every carbon has 4 bonds, so since all the hydrogens are on carbons here, let's label them. There's 2 hydrogens here, 2 here. All these carbons have 2 bonds shown, so the other 2 are hydrogens. Okay, so there's all the hydrogens. We wouldn't give those to you necessarily. I would at least assume you could draw them. All right, so there's 1, 2, 3, 4, and 5. Okay. Do you want me to give you a moment to think about it? Okay. I'll give you about 10, 15 seconds. Which one is the strongest? That's all I want to know here. No order. I want to know the strongest. What'd you get? Some people get 1. That can work. Anybody else get a different answer? 1 and 5 are equivalent. So they're both the same. They're equivalent hydrogen. It's a symmetrical molecule, so 1 and 5 are the same. 2 and 4 are the same also, but they're not the strong ones. Why is that? The longer answer would be there's resonance, meaning if you pluck off one of the hydrogens, say you remove this one and leave a lone pair and a minus charge there, then this will have resonance where the double bond goes there and that goes there. So it'll look like this. There. So that would have resonance. The short answer of it is if you can identify what's called an alpha carbon, hydrogens on an alpha carbon would be the strongest. How do you identify those? Any carbon one away from a double bond will have acidic protons. So if you see, here's the double bond, one away that carbon or one away this carbon, they will have equally acidic protons, and they'll be the strongest. Any questions on that one? Definitely a harder one, but if you got it, very good. You don't have to know now, you just have to know by the test. So we're perhaps here, I guess that's tomorrow morning. Okay, next. All right, let's do this. Acid base and the conjugates. Write that right. Yes, yes, okay, I got it. You should be able to write the acid, write out what's the acid, or identify acid base, conjugate acid, and conjugate base here. Let me give you about 15 seconds if you want a head start to answer that. Acid base, conjugate acid, conjugate base. Five more seconds. Okay, this one. Acid, yeah. Notice it donates the proton. So this is called, yeah, there's a conjugate base. So if that's the acid, this has to be the base. Let's double check. It accepts a proton. So this would be the conjugate acid. So that kind of labeling is what we would expect you to do on an exam. I also want to try one more. Let's see. No, not that. This. Yes. Oh, this is beautiful. Okay, good. I don't want to know the conjugates. I just want to know which one's the acid and which one's the base. In the reactants. In the reactants, all I want to know is which one's the acid, which one's the base. There's kind of two ways you can figure it out. Five more seconds. All right, what's that? That's the acid. So this must be the base. How did you know that these were the acid or the base? Yeah, this, you have to use Lewis definition here because there's no like protons hanging around. So this would be the electron pair donor. And often the base, not always, will have the more negative charge. This would be the electron pair acceptor. So basically this reaches out, grabs the carbon, and the bromine bond gets tossed onto the bromine. So this is the electron pair donor, this is the electron pair acceptor. There's one other, potentially easier way you could have figured it out. OH is a base. Yeah, so it's a base. So by default, this must be an acid. Okay? All right, so that's the identification process. When it's a Lewis acid and base, we probably won't ask you for the conjugates. Doesn't totally work all the time with Lewis. All right, let's talk about the polyprotic. There's only one strong polyprotic that you learned. It's H2SO4. Again, if I asked you to write out the general equation for the acid, you should be able to write plus water goes to HSO4 minus plus H3O plus. You should be able to identify this as Ka1, yep. And then you should be able to take the product and do the same thing again. So you take the product of bisulfate ion, add water, go sulfate 2 minus plus H3O plus. This is called Ka2. Let me ask you a couple things about this. Okay, first, which number is larger, K1 or 2? 1. A little or a lot? A lot larger, crazy larger. Okay? Now in this case, how large are we talking? In this particular example. Yeah, how do you know it's very large? It's a strong acid, so the Ka has to be huge, going or approaching infinity or something like that. It doesn't have to be that big, but we just throw the term infinity around in chemistry. Okay. This one would be small, much less than 1. How would I know that? Because that's not a strong acid. That's a weak acid. Okay. Couple things that you can know about this. What if I asked you for the concentration of the sulfate ion? You would say Ka2, because the entity that has lost 2 protons is always going to be equal to the Ka2 value. The entity that has lost 2 protons, this one's lost 2, is going to be equal to the Ka2 value. What else? Let's say I give you a molarity here. Let's say 0.1 molar of the H2SO4. What method would you use to solve for the pH? Yeah, all you would say is, well, the initial concentration of H2SO4, which was 0.1 molar, is equal to the final concentration of H3O plus. So if that's true, then the pH is the negative log of 0.1. Math majors, what is that number?
13.
Okay, I'll let you just figure it out on your calculator, I guess. It'll be a surprise. All right, anyways, let's do something else. Oh, why does this not contribute to the H3O plus concentration? It's contributing so little. It contributes, but it's so little that H3O plus contributed by the second or future reactions add nothing to the pH. Okay. All right. What else was I going to say? Oh, what if I asked you for the equilibrium concentrations of the rest of the species? Would you need an ice table? Yes or no? Do you need an ice table for any of the other equilibrium concentrations? No. No. The ice table is only potentially used for the first reaction. If the first reaction is a strong acid, you're not going to use the ice table, so by default you wouldn't need it. If this was a weak acid, then yes, you would use it only for the first reaction. All subsequent reactions, you don't use the ice table, you just write the K expression. Let me show you a little summary since we're talking about that. I'm going to go to, I know some other classes don't have this, but I'll just show you what it looks like. This is the end of my AcidBase 2 chapter.
Enderly, I have a question.
Yes, student. Oh, way over there. Hi.
Why is the concentration of the H2SO4 equal to the H3O plus concentration?
Good. That's a great question. I'm going to poll the audience on that. So, why is the concentration of H2SO4 equal to the H3O plus concentration? Strong acid, so what's going to happen to that top reaction on the screen? It'll go forward 100%. So all of the 0.1 that was with the strong acid, at the end of the reaction will be in the products. So you'll have 0.1 of HSO4 minus and 0.1 of the H3O plus. Is that okay, or should I write that out?
Yeah, no, it makes sense.
We're good. Okay. I'm going to show you what's on page 113, and then let's see if I'm going to show more. Yeah, definitely. First, I'm going to show you this. Here's page 113 of my reader. There we go. Here's where we need the ice table. pretty much all equilibrium concentration, like generic equilibrium questions, you'll probably need the ice table. Weak acids, weak bases, salts, ions that are acids and bases, and weak polyprotics. Common ion problems, buffer unless you're using the Henderson-Hasselbalch, and then we're not doing titrations, but for the other fools, when no titrant is added, sorry, with other nice people here, you will suffer tomorrow morning. You should know no titrant added for a weak acid, strong base, or weak base, strong acid, or the equivalence point. Okay? For a weak base, strong acid, or weak acid, strong base. That's where you need it. Okay? All right. One more thing I'll show you at the end of the previous chapter. That's good to review. Here we go. This is page 91 of my reader. Middle of the page here, page 91. You're going to use the assumption that x is small in all these scenarios here at the bottom where my pen is. So, if you have a weak acid or a weak base, or if you have a Ka1 for a weak acid, really those first three are the key ones. In all those cases, x will be small, but only the first three cases would you be doing the nice table. So in all these 1, 2, first three cases, that's where you can use the assumption pretty confident that x is small compared to the molarity it's added or subtracted from. Okay, let's see. Where are we at here? We just did the polyprotic. Any questions before I go to percent ionization? Yes? A weak polyprotic acid. If this was weak, let's poll the audience. How would I solve for the pH? Ice table for which reaction? First or second? First. You write it. So erase this. Just write the ICE for this and solve it as normal. Yeah. Assuming x is small, all of that should reveal. We did that in our class for phosphoric acid, if you want to see the notes. All right, let's go on to percent ionization. Okay, percent ionization. There's really two types of problems, the forward type problem and the going backwards for percent ionization. So here's how that would work. Let's say we give you a generic acid. And you're doing the ice table. Just trying to be kind to people today.
Just today.
Okay. You're going to go through this sort of action. You're going to say Ka is equal to x squared over m minus x, kind of like what we've done before. You're going to say, okay, assume the x is small because Ka will likely be small. You're going to solve for x. And that's going to equal the H3O plus concentration. And then you're going to say pH is the negative log of x. All right, so that would be kind of your typical solving. We could tack onto that a percent ionization problem for fun. So we would say, what's a percent ionization? You go, okay, percent ionization is equal to x over the molarity times 100%. So that would be whatever this value of x will be. It'll be small, divided by m. You multiply that by 100%. So are you expecting a number, expecting 0? Are you expecting a number like 20%, 30%? What percent answer would be normal? Small. How small is small? Less than 10 probably. Less than 10% is a normal answer. It will go up as the concentration changes. So as the molarity changes, that'll drive x forward more than m. So that'll cause the percent ionization to go up a little bit. Okay, the reverse of this goes as follows. So that's a forward. Usually that's the easiest for most students. Where, let me write it like this. Case 1. Case 1. let's see, we would say given M, find percent ionization. The reverse of that, case 2, a different possible way of solving, is to be given the percent ionization, and then you're going to find whatever we're kind of into. That could potentially be M, but I suppose we could ask it in different ways. But let's go in the reverse direction. When you're asked to go the reverse direction, what I would do is set everything up just like I have right now. So let's say it's the second case, and I would just write an M here. Let's say you don't know what that M is at the moment. And then you write this out. But this here, that'll be a number. Okay? Ka will be a number. So you're going to have two equations here. I'm writing this under case 2. The two equations are percent ionization equals 100 times x over m. Okay, so you got that, and you know the percent ionization. The second equation will be Ka equals x squared over m. So you're going to have two equations and two unknowns. Basically what I would do is say solve for x and put it in here. So it's easier than most two equations, two unknowns. You can usually find it right away if you solve for x and then plug that in there. Okay, so that would be a pretty typical reverse direction way to ask it, but that's a different style. There could be other styles, but just to give you a little bit of an idea. Okay, any questions on percent ionization? Next, what is that? Where'd that go? Here we go. Dilute strong acid. Dilute strong acid. Let's do that. Classic case, let's say we have HI, but its concentration is equal to 1.0 times 10 to the minus 9 molar. Here's what you don't want to do. I will write what you don't want to do in blue. You would not say that equals to H3O plus, and then the pH is the negative log of 1.0 times 10 to the minus 9. If you took, we're going to try again. You take the negative log of this number, what do you get? 9. Okay, good. We're on a roll now. Okay, what's the problem with this answer? I don't like it. Yeah, that means it's basic, but this is an acid. What core thing did we miss? It's dilute, and so what does that make happen? When it's dilute, water is a major contributor of the H3O plus. And so water will contribute to the acidity. Okay, so that's the deal. So let's do the short version of this. What would you expect to be the numerical answer that you would get? I'll write this in black here. The pH will be approximately
6.9.
Yeah. Well, I'll write words less than 7, barely. Less than 7, but barely. You could, depending on what this concentration is, I'd expect anything from about, I'm just approximately 6.6 to 6.99. The smaller this number, so smaller compared to the 10 to the minus 7, the closer it is to 6.99. The larger this number, so if it's larger than 10 to the minus 7, then it more drops, like 6.8, something like that, maybe 6.7, etc. So if I was doing a multiple choice, would you do the math? No, that's crazy. Just pick the number, the answer that's less than 7 in that range. If it was a base, you would pick the number that's just barely above 7 in a multiple choice. No math necessary. Okay, any questions about this? All right.
Wait, are we giving them that chemical dilute acid?
Oh, good. What is HI? Let's clarify. I'm going to hold on to this. Strong acid. You'd have to identify that by yourself. So you have to know the strong acid all by yourself. And so thus this goes in the category of dilute strong acid. You know it's a dilute strong acid because you have two components, the acid and dilute, meaning the concentration is, say, 10 to the minus 4, minus 5, minus 6, minus 7, etc. In that pretty small range. It's not 0.1 or 1.0. That would be the non-dilute normal situation. Okay? How do you know what's a strong acid? Yeah, there's a table. Let's just clarify that. Make sure you really need to know this table if it's not burned in your brain from Chem 2A. Yeah, this one right here. That's on 1974. It's also something like that in the textbook. Just to review, because we did what's relatively strong or weak, notice that the strong acids, all the chlorine, bromine, iodine are to the right and down on the periodic table, so we expect them to be strong for that reason. There's a couple others that all have oxygens, the ClO3, O4, NO3, those all have a lot of resonance. So for that reason, those are strong. All the bases are strong. Basically, they're OHs with a metal, which turns out to be a spectator ion, so it's easily ionized. That's why all the metals with the OH are strong bases. Since this is coming up in office hours, let me just add one thing. If you saw CH3OH, is that a base? No, what is it? That's an acid. What's the difference between this and the strong bases that I've listed here? That and this. These are nonmetals. Nonmetals, that's a metal. The metal is what makes it a base. When you have nonmetals here, that OH cannot fall off, only the H can. So it's no longer a hydroxide that is removed. It's just the H. So nonmetals with an OH group actually turned out to be acidic, not basic. All right, next. What is next? We finished that chapter. I think probably the next worst thing is the acid-base 2. Does that sound right? Let's work on that. Okay, acid-base continued. Common ion and buffers, they actually go together. We did in my class a common ion problem first, but common ion problems end up being buffer problems. So they actually go together. Usually when you have a common ion, that makes the entity a buffer. Let me give you an example. Let's say we had HF, and this is 1.0 molar. So the reaction you might write is this. Here's the general equation for an acid. By the way, HF, what kind of acid is it? Strong or weak? Weak, because it's not on the table for strongs. Okay, it's a weak acid. This is 1 molar. Now, let's say, I'm going to write up here above the reaction. Let's say I also added KF. 1.0 molar. So I add KF, the F or the anion match in both. Now that makes it a common ion because it's common to both molecules. Okay, KF is what? Acid, base, or neutral? It's basic. The K is going to be neutral because it's from potassium hydroxide, and the F is a conjugate of the acid. So these two are actually conjugates of each other. So when you add the common ion, you're usually adding the conjugate. Okay, if I add, so let's say I had HF first, and then I add KF. When I add the KF, what will happen to the pH? Go up, down, or stay the same? It'll go up. Why? I'm adding a base. So when I'm adding the base, the pH better go up. Because that's what bases do. They raise the pH. If I add an acid, the pH would go down. Kind of like that. Also, that's pretty much what happens when you add a common ion. The other line of thought goes like this, if you're interested. You add F-. It causes this reaction to shift that way. When this reaction shifts to the left, oh, we got also Le Chatelier right now. This is perfect. That reaction shifts that way. Will the concentration of H3O plus go up or down when it shifts left? Down. So if H3O plus goes down, pH goes up. Yeah, the concentration goes down, the pH has to go up. Should I say more about that relationship, or are you okay?
Good.
Say more or no? No. Okay. I heard more no's, so I'm not. All right. So whenever you have a common ion, that happens. And so when you do the ice table, what's going to happen? I know it's super funny. This is going to get a 1.0 right here. So here's the difference between a normal acid, weak acid question and a common ion. You have a number right there at the common ion. It still shifts this way towards the 0. So the plus X is where the 0 is. Like that. You can go through the ice table. You're going to assume X is small. Same sort of solving technique. However, because this is a buffer, you've got an acid and its conjugate. You, instead of doing the ice table, which I just wrote out beautifully, you could have instead said pH is pKa plus the log of the base of the acid. So you go pKa. Where do I find pKa? Yeah, on my test, on the table in the back. So you go HF right there, 3.18 from the table in the back, plus the log of what number?
1.
1, well, I guess over 1, but let's see where those numbers come from. This one, is that the F- or the HF?
F-.
Yeah. This goes here, and then this one is that one right there. What's the log of 1? 0. Okay. Good, good. I was a little nervous when I asked. Okay. That's going to be 3.18. For Crabtree, that'll be the midpoint where the pH equals pKa of your titration buffer region. For me, that's not till the final. Okay. So you get 3.18. So that would be just a classic buffer sort of problem. Let's review what makes a good buffer. What makes a good buffer? You need 3 parts for a buffer. You need a weak acid and its conjugate, or a weak base and its conjugate. So I'll just write the acid, weak acid and its conjugate base. 2, they need to be of similar molarity. And 3, you need a relatively large volume. That's right. Okay. Now in some questions, 2 and 3 don't come into play per se. But you'll see in my class, you'll see some examples tomorrow. If I saw this pair here, and let's say it's 1.0 molar, is this a buffer? No, that's not a buffer. Why? Yeah, that's not weak. You need it's a strong one. You need a weak one. So it'd be more something like, those molarities don't necessarily need to be the same, they just need to be similar. Something like that would count as a buffer, because you have a weak and its conjugate. If you like to do a harder one, you like it, you're happy?
Harder.
Okay, I was excited about the harder one. Okay. We haven't done one like this in my class yet, but hey, let's have fun with it, whatever. Is that a buffer? Yes.
conjugate.
wanted a harder one, so this is it. Okay. If you don't know, I won't reveal it yet. In this kind of weird scenario, I would write out the reaction. Why am I dropping the K, by the way? It's a spectator ion. It's a conjugate of a strong. Why am I writing the arrow like this? It goes 100%, but why? Yeah, whenever you have a strong acid or base in the reactant, that's this one, it drives the reaction forward 100%. So let's write out the reaction. So the base grabs a proton, the acid loses a proton. Not a reaction that you memorize, just something you have to be able to write what grabs and loses the proton. So let's say this at start was 1.0 and 0.5 and 0. Then the limiting reactant, because it goes forward 100%, all disappears and it adds to the other side. So at the end, you have 0.5, 0, and 0.5. And now what do you have? You definitely have a buffer. It made a buffer because it's 0.5 of the weak acid and 0.5 of the conjugate base. So yeah, this is definitely a buffer. This will happen, this kind of weird scenario, when the concentration of the weak entity is approximately twice the strong entity. It will generate a buffer. Here's the weak entity. The molarity is about twice, in this case exactly twice, of the strong entity. When that happens, it'll generate a buffer. We'll do an example like this in class next time, on Tuesday. Okay, any questions on that? If not, I'll say a tiny bit about Le Chatelier and then let you go. Any questions? No? Okay. Next. Okay. Crazy shows here. Oh, there's this layer in the most awkward position. Okay. Okay. All right. We want to do the shift for each of these. Let's give it a shot. Then we'll go through and I'll make the question slightly harder. Okay? All right. If I add A, shifts which way? Has to go away from what was added, away from the stressor. Add B, no shift, because, yeah, I'm adding a liquid in this case. So you're adding liquids and solids, going to assume relatively no change. Add heat. Right, because, yeah, it's endothermic, so heat would be a reactant. Add a catalyst.
Okay.
Yeah, no change. It just accelerates the reaction, and if it's forward and backwards, say, it accelerates both rates, but it does nothing with equilibrium. It changes what's called the kinetics, which is Chem2C. Increase the volume.
Right.
Yeah, I like the right because, yeah, there's more moles of gas on the right. Only look at the gas. Okay, now let's make this more exciting. If you increase A, let's do an easy one. What will happen to C? It goes concentration to C. Up or down?
Up.
Yeah, because it shifts to the right. If you added A, C would go up. What will happen, just stay on the first one here, to K?
Nothing.
If the temperature is not changing, the K value is not changing. Okay, we'll do one of those, that's fine. That's a good idea. So no change for K. What will happen to Q if it shifts to the right? Goes up or down?
Down.
Well, if it shifts to the right, there's more product. So it has to go up, right? More products over reactants.